11. Last time we were together, we didn't manage to get to the tangent theorems or to cyclic quads. So that's something that I just wanted to have a look at today. Again, probably a good idea to take a screenshot of this. I don't know how big this is. Maybe I can make it a little bit bigger. There we go. All right. So when it comes to tangents, remember a tangent is a line that touches your circle in one place only. Okay, so our tangent theorems are, first of all, the first one, if we have a line that comes from the center, okay, obviously that touches the outside, that would be a radius. If we have got a line that goes from the center, from the radius, from the circumference through the center all the way to the circumference on the other side, then that's called a diameter. Okay, so both of these, irrespective of whether it's a radius or not, if another line touches the circle at that point, as it does over here, the pink line, okay, that would be seen as our tangent because it's touching in one place only. It means that the diameter or the radius will be perpendicular to your tangent. Okay, so we would either use radius perpendicular to tangent, or we would use the reason diameter perpendicular to tangent. Okay, in order to prove that this angle over here at T is equal to 90 degrees. Okay, then the next thing that we are going to talk about, let me just move myself out of the way, is tangents from the same point. Okay, so the common point is going to be this one over here. A is the common point, and we have a tangent that touches the circle at Q and another tangent that touches the circle at P. And what's important for us to notice is that AQ is equal to AP, right? And we say tangents from a common point. Often what happens, not every single time, but often what happens is that these 2 points are then joined, and this angle over here and that angle over there are equal to one another. Anybody remember the reason for that? It was something we spoke about last week, not in the context of tangents, but if you've got a triangle and you've got 2 equal sides, why would the 2 interior angles be equal? Can anybody remember the reason? You could pop it into the chat. It's an important one. Okay, so I'm going to put it, that's it, Nawazi. Angles opposite equal sides. Oh yes, I won't forget to do that. That's fine. Okay, so angles opposite equal sides. So angles opposite equal sides. We'll go and have a look at the homework now, the answers that you were supposed to have. Okay, then the last one, as far as tangents are concerned. All right, so here AT is a tangent to the circle, so there is AT. And inside the circle, we have a chord. And that chord connects to this point over here on the circle. And that chord connects to the same point on the circle. So here what we say is that the angle between the tangent and the chord. So again, here's the tangent, there's the chord. There's the angle between the tangent and the chord is equal to the angle in the alternate segment. Okay, so because the angle between the chord is equal to the angle in the alternate segment, if we have to use this, we refer to it as tan chord theorem. Hopefully that rings a bell as well. Okay, yeah, hopefully everybody is taking screenshots. From last time, this was the question that I gave you that was for homework, wasn't it? All right, so here are your answers just very quickly, and then we'll continue. Okay, so there we go. So you were supposed to say that A was 70 because of the exterior angle of a cyclic quad. In 4.2, in B, you were supposed to get B is 20, but you first had to say that B2 is equal to 90 because of an angle in a semicircle. And then in 4.3, you would have worked out that B1 was 20 because of alternate angles, and you could have worked out that C was 50 opposite angles of a cyclic quad. There's another way you could have done that question as well, using exterior angle of triangle, but that was probably the easiest way to do it. Okay, all right, so there are the answers. You take a screenshot of that, and again, we can talk about things at another stage. All right, so I'm going to move back to where we were, all right, so that we can carry on with this. All right. Oh, all right, Nolwazi, I'll go back. Just give me a moment. There you go. There's 4.3. Okay. All right, let's continue then. All right, let's have a look at this particular question. All right, so here we have been given a circle, ABC, with circle center O. TAN is a tangent to the circle ABC at A, and they've also given us a pair of parallel lines. TAN is parallel to BC. They want us to work out the size of angles A, B, C, and D. All right, so how are we going to go ahead and go and do this? So we don't necessarily have to work in order of the letters, but it's probably a good idea for us to be able to do this. So we can see that we have been given this angle over here, all right? This one here. It is the angle between a tangent and a chord. Okay, so we're going to be able to use tan chord theorem. Let's follow A to the circle. Let's follow C to the circle at B. And there we can see tan chord theorem. So here we would state that A is equal to 58 degrees. Our reason, tan chord theorem. Okay, like so. So we now know that this is 58. Let's pop that in there. Next question, all right, is B. Here's angle B over here. Let's just grab a different color. Here's angle B. Anybody want to suggest a size and an answer for B? Based on what we already know, anybody got an idea? Okay, 116. Okay, that's right. Timbani, where did you get 29 from? Remember, the angle at the center is twice as big as the angle at the circumference. Okay, so if you know the one at the circumference, you've got to double it. Okay, absolutely, quite right. So it's going to be 116 degrees. Reason angle at center equals 2 times angle at circumference. Okay, good job, everybody. Well done. That's great. Yeah, 100%. Okay, very nice. So we now know that that's 116. Now let's go and have a look at angle C. How is angle C related to any of the angles that we already know? Can anybody see the relationship there between something that we already have C is equal to A? It certainly is, Maswazi. What's the reason for it? There we go. Lovely. Well done. Okay, alternate angles. Very nice, guys. Perfect. Okay, so angle C is also equal to 58 degrees. Reason, alternate angles, and then we must not forget to name our parallel lines. Okay, so TN parallel to BC. Excellent, well done. All right, we're nearly there. Let's do the last one. Now they want us to calculate the size of angle D. Okay, so angle D, let's just choose a different color here. Let's go with that. Here's angle D. So that's this little angle in between here. How are we going to work out how big D is? What do you guys think we should do here?
Gilani's hand is up. Gilani might have
Okay.
something.
All right, that's fine. You can welcome to unmute and we can speak. Someone's on the right track in the chat though, which is nice to see.
Ma'am, ma'am, I'm not sure if you can hear me.
Yes, I can hear you perfectly.
Oh, okay. Ma'am, so we got angle C, and so the triangle ABC is, I don't know how to explain it, but B, so okay, 58 times 2 is 160. Oh, okay, sorry, you did get B, sorry. So then all you'd have to do is to get that, I can't even explain it. Okay, you'd have to just, I think also angles in a triangle, like.
Okay, it's actually much, much easier than that. You're right. It is inside a triangle, but this angle over here is also unknown. All right. So if we did want to work in triangle ABC, the problem is that this angle here is also unknown. So then if you see, there's a few people in the chat that have made a suggestion. This line OA is a radius. It is touching a tangent at the circle. So this angle over here is 90. Okay, so angle C plus angle D equals 90. Okay, so what we could say here is that angle D plus angle C, which we know is 58, is equal to 90. Our reason, and that is because the radius is perpendicular to the tangent. Okay, and then all we would need to do now is take 90 away, or sorry, take 58 away, all right? And then that would give us our answer. So we all agree it would end up being 32. Well done, Imrakani. You were very brave to make that suggestion. I understand why you were trying to do that. And that's why I'm glad I'm able to show you this as well, because it would have just saved you a little bit of time. Okay, Lusanda, you've got a question?
Hello.
Hi, Lusanda.
Mom, can you please repeat how you got A?
How I got A? Through tan chord theorem. So if you have a look, what I have done is I have highlighted the tangent and the chord and the angle in the alternate segment. They've all been highlighted in yellow. All right, so here's the tangent, here's the chord, and the chord subtends an angle at the circle in the alternate segment. Okay, so this angle over here and this angle over here are the same because of tan chord theorem. Okay.
Thank you, Mom.
All right, no problem. So now what we're going to do is I'm going to scooch over to the side over here. And here is a similar diagram. All right. I want you guys, sorry, I was just doing some calculations earlier. I want you guys to work out the answers to this. Okay, so hopefully it's big enough. Everybody can see what's going on here. What I will just do to make life a little bit easier for you is let's just go through the information and let's put it onto the diagram just to help you. All right, so again, they've told us that we've got the center of the circle and that O is at the center. So that's this point over here. They've told us that STU is a tangent. So our tangent is over here. Chord BC, so that's this line over here, chord BC, and chord CT, so that's this line over here, are equal in length. Okay, so this leads back to something else that we were saying. last time when we were together, when we've got equal chords, that means something important for us as well. Okay, angle ATC is equal to, let's just get another color. Angle ATC is equal to 105. So ATC, that's this angle over here. This is 105. Let's just pop it in there. Okay, and CTU, that's this angle over here. Let's just highlight that in pink. Angle CTU over here. This is CTU there. That is 40 degrees. Please don't apologize, Amulakani. You were amazing. Okay, don't stress about that. This is not easy at all. Okay, and what's important is that we try. We don't always have to do things right, but we just have to try, and that's what matters. Okay, so I'm going to let you guys do A2. You might need a little bit of help with A1, all right? But I want you to do question A on your own. So question A, work out the size of A2. And what you can do is put your answers into the chat for us. What do you think the size of A2 is? And of course, what is the reason? Very nice. Lovely. Good. Good, everybody. That's great. 100%. Okay, so now A2 is equal to 40. Quite right. Because of tan chord theorem. Lovely. Well done. Okay, so that's that one done. All right, now we're going to do the next one. I see somebody's got their hand up. Good, well done. Prosper, Colin, everybody, that's great. Is there somebody who wanted to ask a question? Is it you?
Lenova's hand is up. I'm not sure, Lenova, if...
Sorry, Yolanda.
No, it's fine. I was waiting for you also to talk. Lenova, you can talk. You can either ask a question or I'm not sure your hand is up, but we are here for you. Try to unmute yourself again. I'm not sure what happened there.
Ma'am.
Hi, Faheen.
Ma'am, can you please explain how do you get to 40 degrees? Because I'm lost here. I mean,
all right, that's
because without working out, how will I get 40 degrees?
Okay. Okay, so Faheen, it is tan chord theorem. That's the reason why. Okay, so over here, you have got, I'm just going to highlight it for you. You have got, let's just get a different color. Let's get yellow again. Here's your tangent. Okay, so TU. T is the point of tangency. Here is your chord, and your chord subtends angle A2 at the circle. Okay, so that's where it comes from. Okay, it's because of tan chord theorem. That's the reason why A2 is equal to 40 degrees. Okay. There we go, Sipasihle. I just explained that again. And Mahle, I just explained that again. I hope you caught that. Let's just see, there's somebody else's whose hands are up. Motibi, you're welcome to unmute.
Okay, guys, we're using a 5-second rule. So if you don't unmute, you can ask after Amkelani. Hey, Mutibi, it's just we don't know whether you're having network problems. So that's why we're not skipping you. Amkelani has a question also. Amkelani, you're welcome to unmute.
Sure. Ma'am, I'm not sure, but for the angle of B1 and 2, I think together, if you say 180 minus 105, then you get that
Yes,
angle because of,
you would. You would. That's
Oh.
lovely. Well done. Okay, that's brilliant. Absolutely brilliant. Because here, what can you tell me about BCTA? What is this thing? It is a cyclic quad. Okay, it is a cyclic quad. Sorry, I shouldn't be writing that using the highlighter. It's probably not very easy to see. Okay, and the reason that it is cyclic is because it has 4 points on the circle. Okay, so BATC, or it doesn't matter where we start, BATC is a cyclic quad. And as far as cyclic quads are concerned, we know that the opposite angles add up to 180 degrees. So if I add B1 and B2 together and I add 105, I will get 180, right? And the reason for that is because it is the opposite angles of a cyclic quad. So let me just do that bit over here. Okay, so in question C, B1 plus B2 plus 105 equals 180, and this is because they are opposite angles of a cyclic quad. Okay, which means that B1 plus B2 is going to be equal to 75 degrees. Now, I know we've skipped one, all right? We've done C, that's fine. Let's go back to A1 again. Anybody got any idea as to how big A1 is going to be? How could we work that out? A1 is this angle over here. Any ideas? This is a more obscure one. Okay, let's see who's got their hands up. William, do you have any idea how we would work out how big A1 is? You're welcome to unmute and speak.
Hi, ma'am.
Hi, William.
Ma'am, I think in order to get angle A1, I think we'd have to combine A1 plus A2 because of the cyclic quad. We'd have to find C1 and C3 using the triangles that we have with the angles that we have so that we can find the opposite angles of a cyclic quad.
You know, William, you're not wrong, but at the moment now, we do not have enough information to be able to work. Well, I suppose actually we do. By the end, we probably would have enough information to be able to work all of that out. But there's actually a much quicker way that's going to save you a lot of time. All right. And this is something that I brought up last time when we were discussing it, but it's not always that easy to see. So what I'm going to do is I'm just going to scooch over here. And yeah, this is what I was drawing earlier. Right. I just want to re-explain something that we were talking about previously. Okay. If I draw myself a circle, all right, and I draw a chord, and from that chord, I have an angle at the circle over here. And I have another angle, oopsie, that's supposed to be a straight line at the circle over here. What can you tell me about this angle in green and that angle in green? What can you tell me about those angles?
Kelani's hand is up. Is that to answer, Kelani? You can give it a try.
Yes, ma'am, that was my answer. Angles.
That's it. They are equal, quite right. Now, Zoom user, who I don't know what your name is, Zoom user, maybe you can tell us your proper name and then we can put it in here. Equal chords subtend equal angles. You're on the right track. This is exactly it. This is what I was trying to get at. Absolutely. Okay, so you've said the right thing there. These angles are equal. Now, imagine I split these two triangles apart. So this is now the same circle, all right? And I've got this chord over here that subtends that angle at the circle. But this chord over here is equal to another chord over there. Those chords are equal to each other. And now I draw another angle at the circle over here. This angle here and this angle here are equal to one another, not because of angles in the same segment, but because of equal chords subtend equal angles. Okay, so it is a corollary of angles in the same segment. Okay, all we've done is that we've split this apart, and this line is now over there, and it's also over here. It's not sitting on top of one another anymore. Okay, so that was a really good spot. Let's go back and have a look at this. All right, so A1 is also equal to 40 degrees. Reason, equal chords subtend equal angles. I'm just going to abbreviate it like that so that I don't end up writing into the diagram. Okay, good job. Well done, Zoom user, whoever you are. That was a really good spot. Okay, hopefully everybody else is okay with that. And now what we can do is we can move on to angle C2, which is this eensy weensy teeny weeny little angle in here, this one. Okay, they want us to work this one out. And this, unfortunately, is a bit of a process. Right, so when William unmuted, he pointed out that angle A and angle C were opposite angles of a cyclic quad. All right, which I think is very helpful. All right, you can certainly do it this way. But in order to work out how big C2 is, what else do we need? We need to know the size of C3 and C1. Can anybody at this point tell me how we could work out the size of angle C3 quite easily? Remember, this is 40 and that's 40. How can we easily work out the size of angle C3?
Hi, ma'am.
Hi there.
Can't we use what's this? The extended angle of AC is actually the C2 is the extended angle of triangle ACT actually.
It is. So, but what we know is that we know that this angle over here is 105. We know that that one's 40. So we can just use angles in a triangle to work out how big C3 is. Absolutely, nice and easy. So we would write over here that C3 plus 105 plus 40 equals 180 degrees because of the angles of a triangle. So how big is C3 then? We would have to take 40 and 105 away. So that would leave us with 35 degrees, if I'm not mistaken.
Yes.
There we go. Good job, everybody.
Yeah,
Now
I agree
we
with
also,
you.
cool beans, thank you. And we also need to work out how big C1 is. Right, so now in order to get C1, we can work out what O1 is. B1 and C1 have got to be equal because OB and OC are radii. So can anybody tell me how big angle O1 is? Again, you can just pop it into the chat. How big is O1? Good, lovely, well done. Okay, O1 is 80. Reason, angle at center is 2 times angle at circumference. Sorry, my spelling went a bit doolally over there. All right, now what we could say, quite right. Now we want to work out B1 and C1. So B1 is equal to C1. What's the reason for that? Why is B1 equal to C1? Again, pop it in the chat. Why is B1? I know they're doing so well. Hey, Yolanda.
Yes, they are. I'm so proud. I'm like just smiling every single time.
Yeah, Amukalani, you're right. They are both equal to 50. Lusanda, angle at center is twice angle at circumference. So BC subtends O1 at the circle, at the center, and it subtends A1 at the circle. Okay, so that means that O1 is twice the size of A1. Okay, that's why it's 80. Angles opposite equal sides. There we go. Okay, so angles opposite equal sides. Okay, so what we can do is we can let C1 be equal to X. So if C1 is X and B1 is X, we would have 2X plus 80 equals 180 degrees. We're working in triangle BOC, angle sum triangle. So that means that 2X would be equal to 100. And as you said, Amukalani, X would be equal to 50. So that means that C1 is 50. We're nearly there. This one was a bit of a process. Not particularly difficult, but just a bit of a process. So now we know that angle A1 plus A2 is 80. So angle A1 plus A2 plus angle C1, C2, and C3 have to add up to 180 degrees. The reason for this is they are opposite angles of a cyclic quad. Okay, like William pointed out for us earlier. Okay, opposite angles of a cyclic quad are supplementary. So here we would say opposite angles of a cyclic quad. And now we can fill in how big these angles are. So A1 was 40, A2 was 40, C1 we know is, oh, sorry, beg your pardon. C1 we know is 50. Let's just put that in. C2 is what we're trying to solve for. And C3 we have worked out was, I think it was 35, if memory serves me correctly. Yes, 35. Is equal to 180. So that means we can now work out what C2 is by taking 40, 40, 50, and 35 away from 180. I think it's going to end up being really, really small. So yeah, so it's going to be 15 degrees, right? Is that what you guys are getting? Yes, lovely. Okay, there we go, 15 degrees. Perfect. Well done, everybody. That's excellent. Good stuff. Okay, so how are we feeling at this point? Thumbs up, thumbs down. Are we feeling good? Good. Oh, wonderful. Oh, I'm so glad.
I'm not sure if Tsogofatso and Lusanda have questions. Their hands are up.
Oh, no problem. Tsogofatso, what's your question?
Ma'am, if I may ask, how would you mark this question?
Oh, that is a very good question, Tsogofatso. So what I would say, a lot of this would end up being marked using statement reason marks. So when we mark geometry, we either use a statement mark, a reason mark, or sometimes something can get statement and reason. Okay, so with something like this, with C3, it's probably be a statement reason.
So don't, okay? It's 15 months back.
So statement reason. Something like this would probably also be statement reason. Then over here, there would probably also be statement reason for that. And then here, 1, 2, 3, I'd say 4 marks, and then here it would probably also be statement reason. So this would be in a matric paper. Okay, in grade 11, they probably would give you, if you were still in grade 11, they would give you a statement mark here and they would give you a reason mark here. But anything that you have done from grade 8, grade 9, easy things from grade 11, so something like tan chord theorem. So in other words, when we worked out that A2 is equal to 40 because of tan chord theorem, it would be just one single mark. Okay, so
because there's 2
statement
there.
reason. All right, or here maybe
This one here is 1 rand because there's 1 and
you
it's
lender.
okay.
So that would be a statement, and then that would be a reason mark over there because it's a little bit more difficult. Okay. You know, I was also struggling to hear. Okay, I know. So I don't know who was talking. Someone was talking. I also couldn't hear what was going on. Anyway, I hope you heard me. All right. Okay, let us move on and go and have a look at something else. Okay, so here things start to get a little bit more difficult, all right, because we're talking about the converse theorems. Is this a little bit small? Do you want me to make it a bit bigger? And then you can take a screenshot. So let's just do that. I'll move this one down. Whoopsie. Make that a little bit bigger. Okay, so there we go. You can take a screenshot of this. Oh, wait, just hang on a second. Before you take a screenshot, sorry, I made a typo here, which I was correcting. Okay, that's wrong. So angle A is equal to BCE. That's supposed to be BCE. There we go. Now you can take a screenshot of that. Okay. Okay, so we've got a screenshot. All right, who's talking?
Ma'am,
Yes, Lucinda.
ma'am, I wanted to know that is it fine every time they give you your circle or your diagram to like highlight your cyclic cards and your triangles so you can know how to work everything out?
Absolutely, Lucinda. Absolutely, you're allowed to do that. Okay, so remember at the end of the year, you're going to take your question paper away with you. So you will have the diagram, which will be on the question paper, and you will also have the diagram for you in a book, a workbook that an answer book that you're going to be working in. Absolutely use highlighters. They are, in my opinion, a vital tool in geometry. Okay, so yeah, very, very important. So now we're going to talk about the converse theorems. And this is something that causes us quite a lot of stress in grade 11 when we have to prove converses. So what's important here is proving that quads are cyclic. And there's 3 ways in which this can be done. So we want to prove that ABC is a cyclic quad, and here we want to prove that it's a cyclic quad, and again here we are trying to prove that the quad is cyclic. These are the 3 different ways, 1, 2, and 3 are the 3 different ways in which a quad is proved to be cyclic. So the first one is, if you can prove that angle A and angle C add up to 180, or if you could prove that D and B add up to 180, then you could prove that the quad is cyclic, and the reason for that is converse, opposite angles of a cyclic quad. Okay, but you have to use the word converse if you're trying to prove that the quad is cyclic. The next way to be able to do it is if you can prove that this angle over here, A, is equal to this angle over here at C on the outside. Okay, so BCE, that is converse exterior angle of a cyclic quad. So if you can prove that angle A equals angle C, so BCE that is, then you've proved that ABCD is cyclic. And the last way to be able to do it is if you have got a bow tie. All right, so if A, B, C, D is cyclic, or A, B, and D are concyclic, or you are able to prove that angle B is equal to angle C, or you are able to prove that angle A is equal to angle D, you can prove that A, B, C, D is cyclic, and our reason for this is converse angles in the same segment. Okay, so those are three very important things. So I've just been asked a question. It's Lee. You said, what does a converse actually mean and why is it necessary to include it in your reason? All right, so it's necessary for you to conclude it in your reason, because what you're doing is an opposite. The word converse means the opposite of. So in other words, the idea here, Lee and everybody else, is that if they tell you that a quad is cyclic, all right, so for example, they give you a circle and they say to you, here we've got a four-sided shape, okay, called T, B, Q, R. Because T, B, Q, and R lie on the circumference of a circle, I can say that T, B, Q, R is cyclic, okay? But if I have a quad like this, and I don't have a circle drawn around it, and let's say this is called A, B, C, D. If I want to prove that it's cyclic, what I'm doing is I'm basically proving that it's possible to draw a circle around it through points A, B, C, and D. That's what I'm proving. It's the opposite. So here you are given the circle with 4 points. The quad is cyclic. Okay. Here, the circle is not necessarily there. Okay, what you are doing is you are proving that it's possible to draw a circle through A, B, C, and D. That's what you are doing when you're proving that the quad is cyclic. All right, and that's why you have to use the word converse. So in this case, if I prove that angle A was equal to angle C, I can prove that there is a circle going through A, B, C, and D, and I would have to use converse, opposite angles of a cyclic quad are supplementary. Okay, but I am going to do an example with you to illustrate this point. Okay, Sia Temba, you've got a question?
Hi, ma'am.
Hi there.
I wanted to ask if do we do converses in grade 12? Because last year we didn't do them. We only did the theorems.
Okay, so you should have done the converses last year in grade 11 as well, when your teachers were teaching you how to prove that quads were cyclic, and it's something that's always going to come up at matric level as well. You're always going to be asked to prove that a quad is cyclic. So yes, it is something that you do need to know how to do. What could have happened is that there are other reasons that people can use, but I don't teach it that way, because if you've learned exterior angle of a cyclic quad, then it's much easier to use converse exterior angle of a cyclic quad than learn a whole new reason. Okay, so maybe that's what it was. Maybe your teachers gave you sort of slightly different. There are some reasons that are acceptable that are slightly different, but it means learning a whole new reason. Okay, so that could, no problem, that could potentially be it. Okay, so let's go and have a look at an example. Okay, let's look here at this one. All right, so we have been given that KLMN is cyclic. We can see that because KLMN lies on the circle that is drawn for us. They also tell us that KM and LM are joined. S and T are points on LN and KM respectively, such that KN is parallel to TS. Prove that LTSM is a cyclic quad. So the first thing that you want to do is go and highlight the quad that they are talking about, LTSM. So LTSM, see, there's a line, there's another line, there's another line, and there we go. Can you see that LTSM does not have a circle drawn around it? So if we want to prove it's cyclic, we're proving that it's possible to draw a circle through points L, T, S, and n. That's what we're proving. All right. What other information have they given us? Well, we already know that KTLM is cyclic. They've told us they've joined this, such that Kn is parallel to Ts. So the minute they tell us that lines are parallel, that becomes significant for us, because either we can use corresponding or alternate angles to prove that things are equal to one another. All right. If you have a look, inside STLM, there is no bow tie. So we cannot use this reason over here, converse angles in the same segment, because there's no bow tie, right? There's no bow tie inside the quad that we're trying to prove is cyclic. So this reason number 3, is out. So either we have to prove that the opposite angles are supplementary, or we have to prove something about an exterior angle. Okay, now, if we have a look, T1 is an exterior angle because it is on the same line as LT. LT has been extended and T1 is on the outside. If I can prove that T1 equals which angle, then I've proved that the quad is cyclic. What does T1 have to equal for this quad to be cyclic? What must T1 equal in order to prove that the quad is cyclic? Anybody got any idea? There we go, M1, quite right. Okay, it has to be equal to M1. So now I can't say that T1 equals M1 because LTSM is not a cyclic quad, is it? I've got to find another way of being able to prove that T1 and M1, for example, are equal to one another. So let me use the other information that I've got. I have got parallel lines. So angle T1, let's just get rid of that because we don't know that they're equal yet. Angle T1 is very definitely equal to what other angle? What other angle could T1 be equal to? There we go, quite right, to N1. So we know for sure that N1 and T1 are equal to one another because they are alternate angles. So T1 equals N1 because they are alternate angles, and that is because Kn is parallel to Ts. Now I want you to go and have a look. Remember we said if we could prove that T1 equals M1, we've done it. Is there a reason why N1 and M1 are equal? What's the reason that N1 and M1 are equal? Can anybody tell us? There we go. Quite right. Angles in the same segment. Excellent. So there you go. The connection between T1 and M1 is N1. N1 is the bridge, okay, that's linking these two together. Okay, so N1 is equal to M1 because they are angles in the same segment. Okay, so angles in the same segment. Okay, so what that means is that T1 equals N1 and N1 equals M1, then it means that T1 has to be equal to M1. That's the deduction that we make. And now we can conclude that LTSM is cyclic. And our reason, converse. Exterior angle of a cyclic quad. Okay, so how would this be marked? Okay, probably here statement reason. Here probably statement reason. Here statement there reason. Okay, so something like that would probably be out of about 4 marks. Okay.
Kamohalo's hand is up.
Sure, Kamachelo,
Yes,
go
sir.
for it.
Hi, ma'am.
Hi, Kamachelo. Sorry to keep you waiting. What is your question?
It's okay. My question is about will we be learning about the converse of the proportionality theorem?
Absolutely. Absolutely. So we're going to talk about the proportionality intercept theorem. Yeah.
Oh, all right. And then my
Yes.
second question was on the part of the where you said that angle N1 is equals to angle T1.
Mm-hmm.
I didn't quite understand that part, ma'am.
Okay, so Kamachelo, it's actually much, much easier than you think. What I'm going to do is I'm going to get rid of all of this, right? And again, this is where our highlighters help us so much. So let's just use a different color. So if you look here, TS and NK are parallel to one another, Kamachelo. Okay, so that means that T1 and N1 are alternate angles. Can you see it now? They are alternate angles.
Oh yes, I can now see it.
Okay,
Thank
you can see it now. Okay, there we
Thank you,
go.
ma'am.
All right, no problem. Okay, how are the rest of you feeling? Are we feeling good? Is it making sense? Are you happy? Good stuff, lovely. Oh, is there another question?
Yes, Lusanda.
Sander, okay, go for it, Lusanda.
Ma'am,
Hello.
since ma'am said angle angle N1 is equals to angle M1 and its angles are in the same segment, right? So meaning K1 can be equals to T.
K1, which angle at T? T1.
No, T2.
No, no. K1, if you're talking about angles in the same segment, then K1 equals N2. That would be angles in the same segment.
Okay, ma'am, thank you.
Okay, all right. Are there any other angles in the same segment here? Oh, I think I see what you're trying to get at. So this angle over here, this would also be angles in the same segment. So this angle over here is not labeled, the one that I've done in green, that would be equal to M2. Okay, that's angles in the same segment. Okay, so we're doing that with our fingers. Okay, let's just have a look what's going on in the chat. Yeah, no, absolutely. All right, so yeah, you just need to keep practicing this. It will become easier. All right, now tonight is, oh, goodness me. Sorry, hang on a second. I'm looking at the wrong thing here. I meant to click on this. Tonight is quiz night, so we are going to let you guys go just a little bit earlier. But again, as always, what I'm going to do is I'm going to give you a question to practice. Now, I don't want you to stress. This question is quite a bit more difficult than the one that we did today, all right? But what I want you to do, right, is just do the first part if you feel that you can't do any more. All right, so in other words, prove that ABCD is cyclic. So what I'm going to do is just move this down again a little bit so that you guys can screenshot it. Okay, there you go.
Tando, sorry. Tando has their hand up. And Tando, was that hand before a question?
Yes, ma'am, I have a question.
Sure.
Good afternoon, ma'am.
Good
Ma'am,
afternoon.
I wanted to ask if we should only include the word converse once we have already found our angles and their reasons in
Yes,
conclusion.
Yes, so you're only going to use the word converse at the end, and that is if you're trying to prove that a quad is cyclic, or if you're trying to prove that a line is a diameter, or if you're trying to prove that a line is a tangent. Then you would use the word converse before you do that. Absolutely. So
Only
when
at
you
the
try
end.
and prove, You're only at the end. So now
Okay,
here we
thank you.
could try and prove that ABC is a cyclic quadrilateral. After you've proved whatever angles are equal, your very last statement has got to be the two angles that prove it. This is what proves it. So proving that T1
Okay.
equals N1 is what proved that it was a cyclic quad because they are exterior angle. Well, the one is the exterior angle of the other. Okay, so because of converse exterior angle of the cyclic.
Thank you, ma'am.
It's
Thank you,
okay.
ma'am.
Pleasure, Tandawethu, no problem. Kamgelo, do you want to ask another question?
Ma'am, I wanted to ask, how do we notice that we're supposed to use a converse theorem? What's that one thing that guides us on the
Okay, so
diagram?
all right, so Kamgelo, you're only using converse when you are proving that a quad is cyclic, a line is a diameter, or a line is a tangent. Then you're going to use the word converse.
All right, thank you, ma'am.
Okay, it's the only times. All right.